Okay, so for 5.6 is really word problems, so there's not really any notes. So I made the handout so you have the problems available. For this first example, you can mark out step B. We're not going to graph any of our exponential growth functions for this section, so we're going to skip that part. But 5.6 is all about exponential growth and decay, and then using exponentials to talk about compound interest. So when you are dealing with business or populations, a lot of times we talk about exponential growth. If you own a business, you definitely want to see exponential growth in your profits. If you have student loans, you definitely don't want to see exponential growth in your interest rate. Unfortunately, that is how they are calculated, and so that's why taking out student loans can be pretty detrimental and should be taken sparingly if you have to. The flip side of that is you can also use compound interest, though, to calculate exponential growth in an investment. So if you take out a bond or a savings account or things like that, you can examine it there. So when we talk about exponential growth and decay, specifically with the population growth in this example, we're going to be using this P of t equals P-O e to the kt. Now, that little 0 is telling you that that is the population at time 0. So that's your starting population. That's what that P-O means right here. See, population at time 0, that's what this part is. Then you have your time, which is usually done in years. And then you have your K, which is your exponential growth rate. We're going to see as we move through this section that even though this looks slightly different than our compound interest equation that we're going to talk about later, it's actually the exact same equation. They use slightly different letters, but it really is the exact same equation. So you're not being asked to memorize multiple different equations. What we're really doing is we're just designating different quantities, as you'll see as we move through this. So you take your initial population, and then we times that by E. That E is not another variable. Remember, this is our number E. And that E is going to be raised to our exponential growth rate times the time. Okay? That's what we're going to use for our population growth, our exponential growth and decay in this section. So let's read the problem. It says population growth in Ghana. In 2014, the population of Ghana, located in West Coast Africa, was about 25.8 million people. So that's kind of where we need to start. That's our PO. And sometimes listing out the parts that you have will help you to plug and chug. Is 25.8. You don't have to put 25, comma 800, comma 000, just 25.8. And the exponential growth rate for Ghana was 2.19% per year. So remember, the K is your exponential growth rate. It is going to give you a percentage, and you always want to convert your percentage over to a decimal. So 0.0219 is going to be your exponential growth rate. And what that means is that Ghana's population is going up by 2.19% every single year. So it wants us to, step A, find the exponential growth function. The exponential growth function will look exactly like P of t equals P-O-E-K-T. It's going to look exactly like this, but we're going to plug in the numbers that we do know. And the only two numbers that we do know are P-O and our K. So step A, we're just going to write our function. P of t equals 25.8 e raised to the 0.0219 t. That is all you're going to do. So you find the exponential growth function. So P of t. Population at time t of Ghana is going to be 25.8 times e raised to the 0.0219 t. Step B, we're skipping because we're not going to graph it. It's not really all that interesting to graph it. Step C is estimating the population in 2018. So in 2018, we're going to use this function that we just came up with, but we need to figure out what t is in 2018. What do you guys think?
4.
Yeah, it's 4, because our starting t, our original date, is 2014. So if we're dealing with 2018, then that means our t is going to be 4. So we're finding p of 4, or the population in year 4 from our starting point, which is 25.8 e to the 0.0219 times 4. You're going to want to type all that in. 28.2 million people. Your homework and quizzes and everything will always be very specific on how many decimal places to round to. Since they told me the original population to 1 decimal place, I'm going to round to 1 decimal place. Part D says, at this growth rate, so we're assuming the rate is going to stay the same, when will the population of Ghana be 40 million? So that 40 million represents our final population. And so what we're going to have is we're going to have 40 million equal to our population function, that 25.8 e to the 0.0219t. Because what we don't know in this step of our problem is we don't know the time. We don't know how many years past 2014 it's going to take for the population of Ghana to hit that 40 million mark. So that 40 million is our end goal. So now we're going to solve. Well, we can't solve yet. We learned how to solve exponentials last class period, but we can't solve yet because our exponential is not completely isolated. To get our exponential, our e, completely isolated, we're going to have to divide both sides with a 25.8. Now, obviously, you're going to be dealing with decimals, so I recommend not using your calculator until the last step or till closer to the end, so that you're not writing out a whole bunch of decimals this entire time. So now we have a fraction equals our e to the 0.0219t. What do I do next? From 5.5, how do I solve an exponential equation like this? There was 2 options. Yeah, we're going to take the natural log of both sides. And the reason we take the natural log over the common log is because we use the natural log 99% of the time. And the common log is only used if the base of our exponential is 10. This is not base 10, this is base e. So we're going to natural log both sides. I can use my power rule to pull that power down on the right-hand side. 0.0219t times ln of e. But what do we know about the ln of e? Yeah, it goes to 1, so it just basically disappears. So if I'm trying to solve for t, what would I need to do next? Yep. ln of 40 over 25.8, all of that divided by 0.0219 equals t. This is when I would recommend, you can't see that, this is when I would recommend using your calculator. Obviously, you're going to have to use some parentheses because you're going to have to put a parenthesis around the top. It'll probably put a parenthesis in there. But the longer you can hold out using your calculator, 1, the more accurate you're going to have your answer, but then 2, you also don't have to write out all these decimals that get really gross really fast. What do you guys get when you type that big bad boy in? 20. T is approximately 20. So in 20 years, or by 2034, depending on how they would ask you the question, is about how long it would take Ghana to get up to 40 million people. Let me get it. Do you have the 36X Pro?
There's a 36X 2S.
Okay. Probably pretty much the same thing. Let's turn it on. Let's see. I'm going to start with a set of parentheses. Where's my ln? Right there. ln. Do you have an ln?
Mm-hmm.
Okay. Then I would put the 40 divided by 25.8. You have to close the parenthesis that closes the 40 to the 25. Then you have to close the parenthesis again because that closes everything that's on top. Divide that by 0.0219. You get 20.02 blah, 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 blah. Does that make sense?
Yeah.
So you kind of have to do the double parenthesis up on top. I don't know if you'd actually need both sets. I'm one that usually sides on lots of parentheses over not enough parentheses because I like to make sure that I know exactly where everything is grouped.
I put ln in front of 40 and 25.
Oh,
28. I think that's where I would go.
gotcha. Other questions? Do you see how that one works? So it's really a plug and chug. I mean, we set up the equation, then we use the equation to figure it out once they tell us how many years, and then the other switch of it for what we did with D is they told us the end population, and we had to come up with how many years it's going to take us to get there. But really, they give you all the bits and pieces, and you plug it in and just solve for what's remaining. We good? All right, let's switch over to compound interest. And I want to point out that with compound interest, our equation is P of T equals principal. That's what the P stands for. I guess I should have written those over here for you. P equals your principal, or the amount you're investing, or the amount of the loan. The R is your interest rate. And your T is your time. A lot of times you'll hear this be referred to as PERT because it looks like PERT. P equals E to the RT. This is specifically for compound interest where it is compounding continuously. But if you compare that with the function that we just did with our population growth, it's the exact same thing. We have a starting amount, or our starting population, or our starting dollar amount. We have our P times E, and then we have it times the rate times the time. It's the exact same thing. They use different letters, slightly different denotations, but really you're using the exact same equation. So you could think about PERT for population growth if you wanted to. You just have to remember that the rate is the which it even says growth rate, so it's still there. If you wanted to simplify that a little bit in your brain. Okay. Compound interest. Suppose that $2,000 is invested at an interest rate of K, compounded continuously, and grows to $2,504.65 in 5 years' time. Okay. That's a lot of information. So we know that our initial investment is $2,000. So that's our P. The rate, they actually don't tell us. They tell us it's K, so that's our unknown. And they tell us that in the beginning, at least, we're going to start with 5 years. So what is the interest rate? That's what we are going to have to come up with. Because we know that after 5 years, we have 2504.65. And to get started with, at least our time is 5. I like to take notes so I don't have to go back up to all the words. There's not a lot of words in this problem, but. So for part A, that's when we're going to plug in all the information we do know to come up with the one piece that we don't know. And in this case, the one piece that we don't know is the actual interest rate, our R. We don't know what it is. We know our P of T, because in 5 years, our principal, the amount of money we have, is going to be 2504.65. And that equals our starting principal, which was 2,000, times e to the r, but we don't know r, and in this kind they call it k, times our time, which is 5. We're going to do the same process we did on the last one when we had to figure out how many, not there, here, when we had to figure out how many years, only this time it's not figuring out how many years, we're going to figure out the rate, because we know the years. But we're going to do the exact same steps that we just did, where I need to isolate my exponential. So I'm going to divide by the 2,000. Equals e to the 5k. Then what do I do? Not yet. Got to take the natural log. Got to ln everything. So ln of 2504.65 all over 2,000 equals ln of e to the 5k. As you get more comfortable with this, if you don't want to write ln e to the 5k because you know it's going to cancel out and you just want to write 5k over there, you totally can. It's not a big deal. If not, you can think about that cancels, or you can apply the power rule and then cancel it however it works best in your brain. Either way, it's going to come down to 2504.65 divided by 2,000 equals 5k. 2504.65 divided by 2,000. All of that is going to be divided by 5 to figure out our interest rate. And you should get 0.045 approximately, which is 4.5%. Questions on that one? We get 4.5%. Okay. So step B is finding the exponential growth function. So we had kind of a more specific example on the step A part. So the function part is where we plug everything in here except for our t, because we're going to get our function in terms of t. So the part B part is where we're going to have P of t equals, our starting principal was 2,000, times e raised to the rate. Well, we just found the rate, which is the 0.045 times our t. So if you were ever asked for the exponential function or anything like that, like, you're always going to have it in terms of the time. So you're going to have P of t equals, and then you're going to have this whole thing over here where t is the variable, the time is the variable that you don't know. Part C, we're going to use that function now that we just found, or we just wrote out, to find what will the balance be after 10 years. So now they're telling us that t is going to be 10. So P of t equals, or P of 10 equals 2,000 e to the 0.045 times 10. And I'll let one of you tell me how much that is to the nearest cent. It is. So after 10 years, at that interest rate, we would have $3,100, pretty much. Now for step D, it says after how long, so that tells you you're going to be finding the time, after how long will the $2,000 have doubled? How do we figure that out? Yeah. Look at you guys. He owes you a Coke now. Yep, we're going to set it equal to 4,000. That's our ending principal. And we're going to figure out our time. So divide by the 2,000 and you get 2. Now we'll ln both sides. And divide by our rate. On the homework and the quizzes, it will specify. I need to look at the problem that I give on the test, and I will tell you on test day. Okay. Safe bet, if it doesn't specify on like the practice test, take it to 1 decimal place. If you're asked to find something. But on test day, I will write on the board how far out to take it. Are there questions on this one at all and how we found compound interest and we found the doubling time and all that kind of stuff? Okay, at the bottom, there is a special box and an additional example of growth rate and doubling time. So there's kind of a shorthand. I mean, we did all of this in step D to find the amount of time it takes to double our investment, but we can actually cut a lot of that out. Because if you notice, if we're doubling our investment, then the first step's always going to be to divide, and when we divide, we're always going to get 2 equals, which means then when we ln both sides, we're going to always have ln of 2 equals the rate times the time. So finding the doubling time, really, in essence, you're taking the ln of 2 divided by whatever the rate is. That's what you're doing to find the doubling time. And either you can memorize that or you can simply work through the problem. It doesn't really matter. But if you like the shorthand, then you have it down here where the doubling time is equal to the ln of 2 divided by whatever your rate is. This time they're giving it to you in terms of growth rate. This problem can have to do with like what we're going to see here, where we're going to talk about the population of the Philippines. There's also a problem where it talks about like the doubling rate of like cats or bunny rabbits or whatever if you're trying to determine population growth in an animal species. This can be helpful so that you can see how quickly it's going to grow. This is obviously a short example because I didn't give you much room. It says the population of the Philippines is now doubling every 37.7 years. What is the exponential growth rate? So this one, we don't know what our K is. So since that's what we don't know, I'm going to lean towards using this middle form of it. We don't know what our growth rate is, but we can take ln of 2 and divide that by the number of years our population doubles by, which is 37.7, and we're going to come up with our growth rate. Type that in, you get 0.0184, which is approximately 1.84%. Any questions on that at all? Why do you raise your hand? Just talk. Okay.
Kind of similar questions to the one I asked before, but this one, who knows what's possible with this?
It will tell you.
Okay.
Yeah. It will always tell you. The reason why the examples that I put on worksheets and in the notes don't specify is because I get them straight out of the lecture portion of the textbook and not out of the problem portion of the textbook. In the problem portion of the textbook, it does tell you exactly how many that you should round to. And that's why on your homework and stuff, it'll always tell you round to the nearest percent or round to the nearest, tenths or hundredths or whatever. All right. Last style of problem, exponential decay. This is where we're going to start talking about like carbon dating and things like that. This could also, I guess, be talked about in terms of like exponential loss. You could look at it that way. Notice, though, that it's the exact same equation that we've dealt with. The only change is we put a negative in front of our rate. Because instead of our population growing or instead of our interest growing, we are losing. We are declining. It is going down. And so there is a negative there in front of your rate. If you look at that little box that I stuck up there, though, that kind of got copied there, the decay rate and the half-life rate, those are the exact same things that we just saw with our growth rate and our doubling time. Nothing changed. And the reason nothing changed is because it's our rate that's changing, and so we don't have to change the formula at all for that. So we've had population growth, compound interest, doubling, and now we're going to see half-life and carbon dating or exponential decay. And even though they're all slightly different, they all use, in essence, the same bone structure for solving these different word problems. So let's look at our problem with this nice text of Dead Sea Scrolls. The radioactive element carbon-14 has a half-life of 5,750 years. Okay, that's a long time. So a half-life. So on the previous section, down here, we used capital T to represent the doubling time, the amount of time it takes for something to double. Here, with decay, we're talking about capital T representing the half-life. How long does it take before you have half as much as when you started? So we have a capital T of 5750 for this carbon-14. It says the percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 that it had at the time it was found. So how old was the linen wrapping? Okay. How old was the linen wrapping? Well, all we know right now is the half time. We don't know anything else. They did not give us a lot of information. But even with this very limited amount of information, we can come up with another key piece. We can come up with what is the decay rate, because we can come up and look at here. When we look at these little equations, all we need is the rate times the half-life. Well, we have the half-life. And if we want to know what the rate is, we can take ln of 2 divided by that half-life, and that's going to tell us the rate at which we are decaying. K equals ln of 2 divided by our capital T. Ln of 2 over 5750. 1, 2, 3 zeros. It's very small. That's why it takes 5,000 years for you to get half as much. So there's our decay rate of 0.00012. Now we know what our K is. So we know what our K is. We know what our T is, but that doesn't really help us because our general equation is P of T equals our starting amount, our starting population, or if you want to think of it like that, e to the negative K over T, or K times T. So we know the K now, but we don't know how much we started with. And we don't know the T because that's what we're trying to come up with. So this one's definitely a bit different than our other problems. And it takes a little bit more thought. So what we're finding is that we are carbon dating. So in the beginning, when we had our original wrapping, the original linen wrapping for this paper, we had 100% carbon in that wrapping. The representation of the carbon there was at 100%. And it slowly decayed over time. So we had 100% carbon at T equals 0. At the very beginning, the carbon was 100%. It hadn't decayed. It hadn't gotten old or anything like that. But we know, according to this, that the Dead Sea Scroll had lost 22.3% of its original carbon. So it's lost 22.3%, meaning we have 77.7% carbon right now in our current state. When they found the Dead Sea Scrolls and they started examining them, we had 77.7%. Now, that still doesn't tell us how much we had to start with. But it tells us that at the time that we're trying to figure out, we had 77.7%. So here's how this is going to look. We had P of T equals P of O equal e to the negative 0.123, like this. This is our general function for this. But the problem becomes that we don't know the original PO. We don't know it. Even after all of this, we don't know it. But we know that however much the PO was, so this is the amount of carbon at time 0, however much there was, whether there was a microgram, or I don't know how you measure carbon, so don't measure this. But, you know, however much you had then, by the time we get to the time that we're looking at now, we have 77% of it. Okay, so we're going to talk about the time now in terms of this. So we're going to have 0.777 of the original amount of carbon. That's what we have right now at the time that we are looking at it. Equals the amount that we start with, e to the negative 0.123. Sorry, I have to count those or I'm never going to get them right. So this problem specifically is different than all the other problems you've dealt with because they don't tell you either the starting amount or the ending amount, but they tell you how much was lost. And so that's what we have to go off of. We lost 22.3% of however much we had, which we don't know yet. And so that leaves us with 77.7% right now of the original. So now we're going to solve. Here's the thing. If we have a PO on this side and a PO on this side, if we're trying to get them together and we divide one of them over, what happens? They cancel. So we have 0.777 equals e to the negative 0.123. We're going to ln both sides and solve it just like we've been doing all the others. So ln of 0.123, divide that by negative 0.123. Lots of repetitive numbers on this one. How many years do we find? So round to the nearest year, approximately 2,103 years old. So slightly different, same formula though that we use anywhere else.